Paris, the 29th of May, 1832. Past midnight, in a rented room, a 20-year-old bends over a stack of paper by candlelight. His name is Évariste Galois, and he is writing against the clock. At dawn, he will walk to a field and stand a few paces from a man holding a pistol, and he does not expect to walk back. So he writes. He does not write a will or a prayer, though he scrawls those too briefly. He writes mathematics. 60 pages in a furious hand, correcting proofs he first drafted at 17. In the margins, he writes 3 words that will haunt the history of science. I have not time. He underlines them. He means it literally. He has hours, not years. What he is racing to save is not a formula, but an idea, a way of seeing that no one alive fully understands. He has found, buried inside every equation, a hidden object he calls a group, a structure of symmetries that decides, before you even try, whether the equation can be solved. It is the answer to a question 3 centuries old, and it is trapped inside one exhausted skull. Twice the Academy of Sciences has lost or dismissed his papers. The most powerful mathematicians in France have read his work and called it incomprehensible. Now, with the night burning down, he addresses a last testament to his friend Auguste Chevalier, begging that the pages be sent to Carl Friedrich Gauss in Göttingen and Carl Jacobi in Königsberg, anyone, anywhere, who might judge them fairly. He signs. He seals the letters. The candle gutters. Outside, the Paris dawn is already gray over the rooftops of the July monarchy, a city 2 years past one revolution and hungry for another. To understand why a boy of 20 writes equations the way a dying man writes goodbyes, you have to go back 21 years, to a small town south of Paris, and to a child who read the geometry of Legendre, the way other children read tales of pirates. Évariste Galois was born on the 25th of October, 1811, in Bourg-la-Reine, a town of a few thousand people just south of Paris. His father, Nicolas Gabriel, was a cultivated Republican who would become the town's mayor. His mother, Adelaide Marie, taught him Latin, Greek, and a stubborn independence of mind at home until he was 12. There were no equations in that first education. There was only a bright, restless boy and a house full of books. In 1823, at 11, he was sent to board at the Lycée Louis-le-Grand in Paris, the same severe school that had once held Robespierre. He hated its cold discipline and its endless drills. For 2 years, he was an ordinary, unhappy pupil, until, at 15, he opened The Elements of Geometry by Adrien-Marie Legendre. He read it, the story goes, like a novel, straight through, cover to cover, in a matter of days, absorbing in one burst what took other students 2 years. Geometry did not intimidate him. It thrilled him. He went next to the original memoirs of Joseph Louis Lagrange, not the textbooks about Lagrange, but Lagrange himself, the papers on the resolution of equations, and the foundations of analysis. A teenager was reading the working notes of one of the greatest mathematicians who ever lived, and understanding them. His schoolwork collapsed in inverse proportion. Teachers complained that he was distracted, secretive, original, to the point of insolence. One wrote that he was under the spell of mathematics, another that his ambition was excessive. He stopped showing his steps because the intermediate work bored him. He saw answers whole and refused to condescend to the page. By 17, he was doing original research, and in 1829 he published his first paper on continued fractions. But his mind had already fastened on far larger prey. He had begun to circle the one problem that had defeated every mathematician since the Renaissance, a single stubborn equation that no formula on earth could crack. To see why it mattered, you have to understand what solving an equation had meant for 300 years. For 3 centuries, algebra had been a story of triumph. Babylonian scribes could solve quadratic equations, degree 2, 4,000 years ago. In the 1500s, Italian mathematicians cracked the next 2 levels in a burst of feuding brilliance. Scipione del Ferro and Niccolò Tartaglia found the cubic, degree 3, and Lodovico Ferrari conquered the quartic, degree 4. Each solution was a formula built from the equation's coefficients using only addition, subtraction, multiplication, division, and roots, what mathematicians call solving by radicals. Then progress stopped. The quintic, degree 5, with its innocent x to the 5th power, refused every attack for 250 years. Leonhard Euler tried and failed. Lagrange, in 1770, studied why the old tricks worked and sensed that for the quintic they must break down, but he could not say why. In 1824, a young Norwegian, Niels Henrik Abel, proved the shocking part. There is no general formula in radicals for the quintic. It cannot be done, ever. But Abel's proof told you the wall existed, not where the door was. Some 5th-degree equations can be solved by radicals. Most cannot. What separates them? Why is x to the 5th minus 1 solvable while a generic quintic is not? That was a question no one had even known how to ask properly. Galois asked it, and he inverted the entire problem. Instead of hunting for a formula, he studied the equation's roots as a set of objects that could be shuffled among themselves. Some rearrangements, called permutations, preserved every true relationship between the roots. Others did not. The collection of the ones that did formed a structure, closed and self-consistent, that he named a group. The size and internal shape of that group, he realized, was the equation's fingerprint. If the group could be broken down in a particular stepwise way, the equation was solvable by radicals. If it could not, no formula would ever exist, not because mathematicians weren't clever enough, but because the symmetry itself forbade it. It was a breathtaking leap. An unsolvable equation was really a statement about a hidden object. Now the boy had to make the world listen, and there his real troubles began. In 1829, Galois submitted his research on the solvability of equations to the Academy of Sciences in Paris, the highest court of French mathematics. The manuscript was handed to Augustin Louis Cauchy, the most prolific mathematician of the age, and exactly the man to appreciate it. Cauchy was supposed to report on it. He never did. He mislaid the memoir or set it aside, and Galois' first bid for recognition simply evaporated. He tried again. In February 1830, hoping for the Academy's grand prize in mathematics, he wrote out his results and submitted them to the secretary, Joseph Fourier. Fourier took the manuscript home to read it. In May 1830, Fourier died, and the memoir was never found among his papers. Galois' masterwork, the summary of years of thought, was lost a second time, now in a dead man's study. The prize went to Abel and Jacobi. Galois' name was not even mentioned. The pattern was becoming unbearable. In January 1831, urged on by Simeon Denis Poisson, he submitted a third version on the conditions of solvability of equations by radicals. He waited months. In July 1831, Poisson returned his verdict. The reasoning was not sufficiently clear, nor sufficiently developed for the Academy to judge. Incomprehensible. Poisson suggested he expand it and resubmit. It is easy, now, to blame the referees. But Galois wrote for readers who did not yet exist. His notation was compressed, his leaps enormous, his patience non-existent. He expected the reader to see what he saw. The theory of groups he was using had, in effect, been invented by no one but him. He was handing the Academy the answer key to a language he had written alone. To a proud, grieving 20-year-old Republican who already felt the establishment was rigged against him, each rejection landed not as criticism but as proof of a conspiracy. The mathematics was being buried alive, and around him, France itself was catching fire, barricades in the streets, a king falling, and Galois, humiliated by the men of science, was about to throw himself headlong at the men of power. Grief lit the fuse. In July 1829, Galois' father, Nicolas Gabriel, hounded by a malicious priest's forged letters, killed himself in Paris. Weeks later, Évariste sat the entrance examination for the École Polytechnique, France's most prestigious school and the beating heart of its Republican student life, and failed for the second and final time. Legend says he threw the eraser at an examiner who irritated him with a foolish question. Rejected by the school he wanted most, robbed of the father he loved, he turned his fury outward, toward politics. The timing was combustible. In July 1830, the Three Glorious Days toppled Charles X, and while the Polytechnique students marched in the streets, Galois was locked inside his own school by a director who bolted the gates. He never forgave it. He enrolled at the École Normale, then was expelled in December 1830 for a letter attacking that same director's cowardice. At 19, he had no father, no school, no academy, only his republicanism, which he now embraced with the whole of his reckless heart. He joined the radical artillery of the National Guard, a unit soon disbanded as a threat to the throne. On the 9th of May, 1831, at a Republican banquet, he raised a toast while holding a knife, an apparent threat against King Louis-Philippe. He was arrested the next day and, remarkably, acquitted. Freedom lasted a month. On the 14th of July, 1831, Bastille Day, he was arrested again, wearing the band guard uniform and carrying weapons, and this time sentenced to 6 months in the prison of Saint-Pélagie. Prison did not stop the mathematics. In his cell he kept working, revised his rejected memoir, and wrote a bitter, brilliant preface raging at the academicians who had ignored him. Fellow inmates recalled a slight, intense young man who drank little and calculated constantly. He survived a cholera outbreak and was moved to a nursing home in the spring of 1832. There, newly released and barely 20, he met a young woman named Stephanie and stumbled into the quarrel that would put a loaded pistol in another man's hand. May 1832. Galois is barely out of prison, released from Saint-Pélagie into a Paris, still smoldering with Republican rage. He is 19, going on ancient, sick, broke, and in love. Her name, as far as history can recover it, is Stéphanie Félicie Poterin du Motel, the daughter of a physician at the boarding house where he convalesces. What passed between them nobody knows for certain. Fragments of her letters survive in Galois' own copied hand, cautious, cooling, telling him to stop. Whatever the wound, it festered fast. By the last week of May, a quarrel had hardened into something no apology could undo, a challenge to a duel with pistols fixed for dawn on the 30th. The identity of his opponent is still argued 2 centuries later. Some name Péchaud d'Herbainville, a fellow Republican. Some suspect a police provocation engineered to silence a dangerous agitator. Some read the whole affair as a matter of honor over Stephanie, and nothing more. Galois himself blamed no conspiracy. In letters dashed off on the 29th, he wrote that he died the victim of an infamous coquette, that he was dragged into a fight he could not refuse, that 2 patriots had quarreled and one must fall. To his Republican friends he begged forgiveness for dying by such a stupid cause, for a cause so contemptible. There was no talk of practicing his aim, no arrangement of seconds who might halt the thing. He seems to have believed with grim certainty that he would lose. A 20-year-old who had already outrun Legendre and Lagrange, who had asked why the quintic resists every formula, now counted the hours until a field outside Paris and a single loaded pistol. He did the arithmetic of his own life and found it short. So he turned that final night from the woman and the weapon to the only thing he trusted to outlast him, the pages of mathematics no examiner had yet understood. If the morning took his body, the ideas must not go with it. He sat down and began to write against the clock. The night of the 29th of May belongs to the manuscripts. Galois spreads out 3 years of rejected work, the memoir Poisson called incomprehensible, the theory of equations, the scattered notes, and begins editing his own legacy in a race he knows he is losing. He writes a long testament letter to his friend Auguste Chevalier, dated that night, and it reads like a man emptying his mind onto paper before the lamp gutters out. He lays out the conditions under which an equation is solvable by radicals. He sketches the groups that govern permutations of its roots. He gropes toward what would later be called the theory of ambiguity, ideas about integrals and functions that mathematicians would not fully catch up to for decades. And in the margins, again and again, he scrawls the same desperate note: Je n'ai pas le temps. I have not time. The phrase becomes a heartbeat running down the pages, beside crossed-out lines and hurried corrections. Wherever a proof would have taken an hour he did not own, he is not writing for the academy that lost his work. He is writing past it, over its head, to the only judges he still believes in. He asks Chevalier to make his results public and to send them to the two greatest mathematicians alive, Carl Friedrich Gauss in Göttingen and Carl Gustav Jacobi in Königsberg. Let them, he says, not decide whether the theorems are true, but whether they matter. L'importance de ces théorèmes. It is a staggering act of faith from a 19-year-old with hours to live, the certainty that somewhere is a mind large enough to see what Paris could not. He signs, he seals, he sets the papers in order, 60 pages, give or take, holding a new kind of algebra that no one on earth yet fully understood. Outside, the sky over the city begins to gray toward the 30th of May. Somewhere a field is waiting, and a second is loading a pistol. Galois blows out the lamp and goes to keep his appointment. At dawn on the 30th of May, 1832, in a field on the outskirts of Paris, the pistols are raised. A single shot finds Galois in the abdomen. His opponent walks away. The seconds scatter. He is left on the ground, alone, until a passing peasant discovers him hours later, and he is carried to the Cochin hospital. There is no antisepsis in 1832, no surgery that can repair a gut wound, only fever and the slow certainty of peritonitis. His younger brother Alfred reaches his bedside in tears. Galois, holding on, tells him not to cry. I need all my courage to die at 20. On the 31st of May, he is gone. He is buried, without a stone, in the common trench of the Montparnasse cemetery, and the grave is lost. So too, it seems, is the mathematics. Chevalier does exactly as he was asked. He copies the testament letter, publishes it that September in the Revue Encyclopédique, and sends the papers outward. Gauss never responds. Jacobi never responds. For years, the 60 pages sit unread, a dead man's handwriting no one can decipher, filed among the effects of a failed rebellion. And then the resurrection. In 1843, the mathematician Joseph Liouville takes the manuscripts in hand and does what Cauchy and Poisson would not. He sits with them, line by line, until the fog burns off. What he finds astonishes him. He tells the Academy that Galois had solved, completely incorrectly, the question of when an equation can be solved by radicals, that the reasoning was as rigorous as it was original. In 1846, 14 years after the duel, Liouville prints the papers in his Journal de Mathématiques Pure et Appliquée. The voice that Paris had silenced in a field at dawn begins, at last, to speak. Not from a hospital bed, but from the page, to every mathematician who would come after. What Galois had scrawled against the clock was no longer the ravings of a doomed boy. It was a doorway, and the mathematicians of the century were about to walk through it into a world no one had known was there. What Liouville unlocked was not a trick for solving equations. It was a new way of seeing them. Galois had noticed that the roots of an equation are not a helpless list of numbers, but a company with its own internal order, that you can shuffle those roots, and only certain shufflings leave every true relationship among them intact. Collect those permissible shufflings and they form a structure that closes on itself, that composes and inverts like a private arithmetic. He called it, for the first time in this sense, a group. The quintic resists every formula, not by accident, but because its group is too tangled to be pulled apart in the layered way that radicals demand. The old 3-century wall suddenly had a reason behind it, written in the language of symmetry. From that single insight, an entire architecture grew. Galois theory turned into abstract algebra. Groups became the mathematicians' universal grammar for anything that can be transformed and yet stay itself. Physicists found the same structures beneath the conservation laws of the universe. Noether's theorem, the symmetries of crystals, the gauge groups that organize the particles of the Standard Model. Cryptographers built the security of the digital world on finite fields that still carry his name, the Galois fields humming inside every encrypted message and error-correcting code. The boy who died at 20 in an obscure duel, whose grave was lost, and whose papers gathered dust for 14 years, turned out to have handed the future one of its master keys. The lamp he blew out over 60 scrawled pages lit a path that runs through modern algebra, quantum physics, and the machines we trust with our secrets. And it all began with a question deeper than how, asked in the margins of a life running out of time. Not how to force a solution, but why some structures yield and others never can. The answer he left behind, in the trembling hand of his last night, still stands as the thesis of everything that followed. Symmetry is the hidden language of equations.